Hello and welcome to my demonstration today that will cover MBSE integration and how to connect your descriptive models to your analytic models in order to verify requirements. My name is Justin Williams, and the mission that we'll be going over today will locate wildfires on the ground and then relay the location of those wildfires back to a couple ground sites. The way that this mission is designed is that there are two constellations of satellites that will be used. The first constellation is the sensing constellation seen on the left. This consists of 9 simple CubeSats that basically just have a sensor on them. They look down at the ground to try to locate the fires. However, these satellites don't have any onboard memory, so in order to relay the location of those fires back down to the ground sites, they must have constant contact with the communication constellation, which you see on the right-hand side. This consists of about 50 satellites, which will take the location from the sensing satellites and downlink them to the ground stations. Along with this, our customer has given us 4 requirements, and the 4 requirements are that the sensing system shall collect imagery with a ground sample distance less than 6 meters in order to detect any wildfire in North America greater than 1 acre. The communication system shall provide link availability with less than 7.5% outage. The overall system revisit time shall be less than 4 hours, and the total cost of the entire system shall be less than $130 million. And luckily for us, another engineer has already done the constellation design and verified requirements 2 and 3. What's left for us to do today is look at the sensor that's on board the sensing constellation and choose a sensor that will verify requirements 1 and 4. To summarize, during the demonstration today, we will be choosing a sensor from a sensor catalog that we'll look at in a few minutes. What's important to note during this demonstration is that the mission is still in the preliminary design phase. At the end of the demonstration, I'll be showing you ways that you can increase the fidelity of your system once you choose the right design variables. For today's mission, we are using Cameo as the SysML tool, which will track our requirements and serve as the descriptive model for the system. If you're unfamiliar with what a descriptive model is, it is a model that describes what the system looks like. It allows us to see how the system is broken up from an architecture standpoint, and we can also add in any requirements that the customer gives us so that we can see everything in one place. So here we're looking at the architecture breakdown, but then also on the requirements section, we can see the 4 requirements that the customer gave us are all included in this one descriptive model. In your mission, your descriptive model is probably much more developed than ours is today, but again, the mission is meant to be in the preliminary stages, and more information will be added once we start making some key design choices. In today's demonstration, we will be linking together our analytic model, or our mission model, which will be STK, and we'll link that directly to this model in Cameo in order to verify that we're meeting those 4 requirements from the customer. We'll come back to Cameo at the end of the presentation. I just wanted to highlight it here to show that we have a descriptive model set up for us and give everyone an idea of what that model might look like. Now we'll go into our mission model, STK. For anyone who may be unfamiliar with STK, STK is a modeling, simulation, and analysis platform that allows you to evaluate the performance of engineered systems in a mission environment. Today, it will be doing all of the complex calculations that we see throughout the presentation. We are currently looking at what you would most likely see whenever you open up a new STK scenario. Here we have the Earth. We can rotate it left and right. We can zoom in. We can zoom out. On the left-hand side, we have our object browser. And the object browser contains all of the objects that are needed in this scenario in order to complete our mission today. Throughout today's STK portion of the presentation, I will be using a UI plugin called Operator's Toolbox on the right-hand side. I will just be using this to jump to and from certain views that have different objects turned on and off, but it speaks to the flexibility of STK. If you're interested in creating your own UI plugins, our help documentation online has plenty of information about how to connect to STK's open API. You can also use that information or get in touch with us and we can help you create your own tool inside of STK. So as I've mentioned, the purpose of today's mission is to locate the wildfires on the ground. So if I jump to a view here, we can see the area of interest. And the area of interest is going to be North America and predominantly in the Mexico and United States region. Here we can see a whole bunch of pink dots on the ground, and what these pink dots represent is the location of each wildfire. Along with giving us the requirements, the customer gave us a shape file that we were able to insert into STK, and that shape file had the location of every wildfire in North America at the time. This is important because we can see where they are now, but also if the customer wanted to redo their analysis 3 years from now, they would just have to provide us with a new shape file, and that way we can ensure that we're meeting their requirements with the most current and up-to-date locations. Along with the fires, we will see 2 ground stations. One is in Sioux Falls, and the other one is in Gilmore Creek. So when the sensing constellation views the wildfires and sends it to the communication constellation, that information will get downlinked to one of these 2 locations. Now I'll jump to a view that shows how we're going to achieve this mission. In this view, we can see 2 satellites. One satellite is in the white constellation. This is the sensing satellite, and this has the sensor that looks down at the Earth, and you can see the field of view of that satellite. The other satellite we have is in the blue constellation, and it's just this little dot, and this just represents one of the many communication satellites that we have in this mission. What I'd like to do now is take a closer look at the sensing satellite to get an idea of what we're really trying to do here when we choose which sensor is going to be on board. So we can go into the properties of the sensing satellite, the sensor on that satellite. And we can see here that it's just a basic rectangular sensor that has a vertical half angle, horizontal half angle of 45 degrees and 35 degrees. The key parameters that we're going to be interested in today are going to be on the resolution tab. And these are going to be the parameters of focal length and detector pitch. The reason that we're interested in the focal length and detector pitch are because these are the 2 key parameters that are involved in ground sample distance, which is that metric that we had in our first requirement. If you remember, we need to get our ground sample distance less than 6 meters. And so by varying the focal length and detector pitch, we will be able to do that. If at any point in time in STK you're looking at a panel and you don't know what all the information on the panel is, you can use our context-sensitive help pages. And if you just hit the help page, then the help pages will go directly to where you can find out more information about that particular topic. So here we can see that we were on the sensor resolution page. I hit the help button, and now the help has gone right to the sensor resolution. Now we can read the definition for the sensor resolution, and this says that to define an optical sensor's resolution, you must specify the focal constants, focal length, and detector pitch. These constants are used in the computation of ground sample distance for the sensor, and ground sample distance is computed as follows. So we can now zoom into this area here, and we can see exactly how focal length and detector pitch go into our ground sample distance computation. In order to minimize this ground sample distance and get it less than that 6 meters, we're going to need to maximize our focal length while also minimizing our detector pitch. Doing this will result in a smaller ground sample distance. We can also see a visual diagram that illustrates what ground sample distance is and exactly how each of these components play into the calculation. Now I'd like to go into the sensor catalog that we'll be using in order to see what the different options are that the customer has given us for the sensors. So here we can see 8 different options that the customer has given us, sensors A through H, and each sensor has an associated focal length, detector pitch, and cost. So the trade study that we'll be varying today will be on focal length and detector pitch, but of course we also have to keep in mind the cost of this system. And so we have to pick one of the sensors that won't go over the budget that we have. That cost will go into another model that we have. Again, this is a preliminary model, but the cost of the sensor will be input into this spreadsheet, and that will determine whether or not we go above or below our $130 million cap. And now we can take everything that we've seen so far and combine it all together to see how the mission actually operates. So here we can see that we have our satellite. It's pointing down at the ground, and each one of the wildfires that is being illuminated or is inside of the field of view of the satellite has a green box around it. This is just a basic figure of merit that shows that we should be able to see this fire. However, with the current sensor, we probably don't have the ground sample distance required in order to actually see these. So here we can see that the satellite is viewing the fires. It sends that information to the communication satellites. The communication satellite will then downlink that information to the ground station. And each of these lines is a line of access in STK. And what that essentially means right now, and the way that we're using it right now, just means that these satellites have line of sight with each other and then also with the ground site. Again, this is the beginning of the design process, and as we start to get deeper into this design process, we will start adding in communications, and this will not just be line of sight, but it will also have communication thresholds and things like that associated. We can also use STK to view how this mission looks going forward, and we can see that these wildfires, as they become illuminated, are being lit up with green, or they're not illuminated anymore. We can go forwards and backwards here just to view. Now that we've seen how the mission is going to operate and we've seen the sensor catalog, we can go into ANSYS ModelCenter in order to see how we're going to run our trade studies and finish the analysis for this mission. The easiest way to think about ModelCenter is that it's a conductor and an orchestra. In an orchestra, certain instruments need to be played at certain times in order for everything to come together nicely and sound really good. And ModelCenter basically takes that same idea and applies it to the models that are in its own workflow. It allows the user to define inputs and outputs for each model and allows the data to pass through the entire workflow. For example, in our case, we're going to be changing the sensor option A through H. And depending on which sensor we choose, it will go into, depending on which sensor we choose, it will start the workflow and go into the sensor catalog that we just looked at in that Excel spreadsheet, and it will pull the detector pitch and focal length values out. It will then use those values and plug it into the STK scenario that we looked at. And in the STK scenario where we saw the focal length and detector pitch, it will run through all of the analysis with those values. And then at the end, we will have a total cost, a ground sample distance, our system outage percentage, and our revisit time. So ModelCenter can be used as a tool in order to connect other tools together and create a workflow just like we're seeing. Or ModelCenter can also be used as a trade study tool in order to run an analysis on which sensor may be the best option for us to use. I've gone ahead and run this trade study ahead of time to save time during this demonstration. So here we can see the trade study after it's been run to completion. And we can see sensors A through H and each of the 4 parameters that we care about based on our requirements. If we wanted to, we could go through each one of these columns and see which one we think would be the best one, or we can use an added view that ANSYS ModelCenter has for us in order to view this data in an easier way. I've now added in a 3D scatter plot where on the x-axis we have the sensor option A through H. On the y-axis we have the ground sample distance of each sensor, which goes from 2 to 16. And on the z-axis we have the total cost of the entire system using these sensors. And so here we can see that we need a ground sample distance of less than 6 meters. So here's the 6 meter line, and we need something that's less than $130 million. So we can kind of eyeball these if we wanted to, or we can go to the constraints that ANSYS ModelCenter allows us to have, and we can put maximum constraints on these. So for the ground sample distance constraint, we can use 6 meters, and for the total cost, we can use $130 million. And once we click out of here, we'll see in the top right-hand corner that ModelCenter has grayed out any of the infeasible options. And so here, out of the 8 sensors that we started with, we only have 2 feasible options. If we hover over either one of these options, we can see more information regarding them. So for example, for sensor G, we can see the ground sample distance, the total cost, and we can also click on this ellipses, and the ellipses will show us all of the information pertaining to this design point. For the rest of the demonstration, I'm going to be using sensor D because it verifies our requirement of less than 6 meters of ground sample distance, and it's also cheaper than the sensor G. Now that the information from STK has been flowed into ModelCenter, we can take the data from our mission model, or STK, and now connect it into our descriptive model inside of Cameo. So let's go back inside of Cameo and see how that works. To view that same type of information, we can open up ModelCenter MBSE. ModelCenter MBSE is a plugin to Cameo and allows the user the choice of which variables from the ModelCenter workflow they want to share and open to Cameo to verify their requirements and their system design. We can go into the analysis on the right-hand side of the wildfire ModelCenter workflow that we had. On the left-hand side, we can see the entire Cameo structure broken out into the structure model. And on the right-hand side, we can see all of the analysis variables that we decided to pass from ModelCenter into Cameo. So here you can see revisit time and total cost, just as a couple parameters that we decided to pass through. And we can see how those connect to the overall Cameo model. Once you have all of your parameters linked to value properties inside of Cameo, you can then run your analysis. So here we can see that we have an execution plan, and in this execution plan, we can vary certain parameters in order to run analyses just like we did in ModelCenter. So for example, if I click on this sensor D, I have the option to change it between sensors A and H, and depending on which sensor I choose and which analysis I run, then I will get different results. So if I choose sensor B, for example, and hit run, and I've done this ahead of time, now after that process runs, I will have all of the information related to sensor B available to view. So all of the parameters that we passed from ModelCenter into Cameo are now here and available to view. Along with this, and the key reason for using ModelCenter MBSE is because we can link ModelCenter MBSE to the requirements that we had earlier. So here we can see the requirements that we had, and in this scenario, it's very simple because we only have 4 requirements. But on your program where you might have over 300 requirements, it would be very nice to see which requirements you passed and failed just by a quick glance. In this case, we can see that sensor B satisfied revisit time, total cost, and our comms outage, but it failed that ground sample distance requirement. And we can see that it failed it by 3.46 meters, which means that the ground sample distance for sensor B is around 9.4 meters. However, if we came back to our execution plan and just changed this to sensor D and ran the analysis here, the results for sensor D will show that we actually passed that ground sample distance requirement. We can see that this is a viable option for us to use going forward. Now that we've chosen the sensor, we can take the results of this sensor, push them back into STK, and start to increase the fidelity of our system and the mission that we're working on. So now I've opened up a scenario that is the exact scenario that we saw before, but the only difference is that I've changed the values for detector pitch and focal length. So now we can go into the sensors of one of the sensing satellites just to view that the values have been updated. Here on the resolution tab, we can see that the focal length is 0.29 meters and the detector pitch is much smaller than it was previously. With a satellite that has now been chosen, we can increase fidelity of the system by taking all of the information that we'll know about that sensor and adding it in. Instead of having a rectangular sensor, for example, we can change this to EOIR, and on this EOIR page, we can increase our fidelity by adding in spatial, spectral, optical, and radiometric parameters. Again, if you're ever confused on what any of these parameters are, or you don't know what they are, you can either contact us or hit this help button, and this will open up the context sensitive help, which will be very helpful. One more way that you can increase fidelity, and the last way that we're going to cover today, is by adding in that communication system that I had talked about earlier. So up till now, everything has just been a line of sight. Can one satellite see another satellite? However, if we zoom to one of the communication satellites, we can see that it has an access line to the sensing satellites. So in order to add more detail to this scenario and make it more accurate, we can add in the detailed antenna patterns. So here we can see just a parabolic antenna, and this is the gain pattern, and I've sized it up just so that we can see it better for this demonstration. We can see that this is an ideal antenna, however, and if we wanted to make this even more realistic, we could use ANSYS HFSS in order to bring in the far field pattern of the sensor on board the satellite, which is very different. Here you can see the actual onboard far field pattern and the antenna pattern of this sensor on board the satellite based on the geometry of the satellite that we have chosen. The reason that you might want to increase the fidelity like this is because if we open up just a simple signal to noise ratio graph between these two satellites and we zoom in to an area of interest, we can zoom in here and see that if we were modeling our entire mission with just the idealized parabolic antenna, then we would expect the results that we have here on the green graph. However, if we're using the real antenna from HFSS, taking into account the body of the satellite and all other aspects of the mission, then we'll notice that we actually have a system outage between these two satellites between this time. Maybe that's okay for your mission, and maybe it's not, but if your mission really requires this to have 100% satisfaction intervals, then you're going to want to go through that same trade study that we just did, but this time varying communication instead of varying the focal length and detector pitch. Also, STK allows you to view this. If we zoom in here, we can see that this line connecting the access between the two satellites is actually going in between two of the lobes of this antenna pattern, and that's the reason that we're getting that outage. That's the end of my video, and reach out if you have any questions. Thank you for watching.